Hello, today we're going to talk about the ideal gas and the ideal gas law. What is an ideal gas? Well, you might remember back on one of the very first videos, I went over with you the KMT, the kinetic molecular theory, and that pretty well defined for an ideal gas. And so part of that KMT said that gases are made up of particles that are so small compared to the volume they occupy, we consider them to be volumeless. And probably the falsest part of that statement, they exert no attractive forces on one another. Well, from January school, we learned that there's nonpolar molecules and there's polar molecules. Well, nonpolar molecules don't attract each other as much as polar molecules do. So especially if you have a polar molecule, it's going to be less than ideal. Ideal gas law works well for gases with large volumes and low pressures. Why these circumstances? These are the ideal circumstances because that's where they can be the furthest apart and therefore have little attractive forces. And so that's your ideal gas. Avogadro's hypothesis states that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. And we actually have a standard molar volume, and that is that the volume of 1 mole of any gas at STP, recall STP, standard temperature and pressure, and that would be one of our standard pressures. Let's go ahead and just use 1 atmosphere and standard temperature of 273 Kelvin. And so the standard molar volume is 22.4 liters when you're at those conditions and you have 1 mole of the gas. The ideal gas law takes into account the Boyle's law, Charles' law, and Avogadro's hypothesis. So you have Boyle's law that pressure times volume was equal to K because they're inversely proportional. You multiply the two variables. And then Charles' law, which was a direct proportion, V equal KT. Remember, it's a linear graph. And so that K value would be the slope of that line. And then Avogadro's hypothesis is saying they're directly proportional. The more moles you have, the more volume it will occupy. And so if you combine all of those, you get PV equal NKT. So you just kind of put them all together and get that. Well, what we do is we take the K out and put in the letter R anyway. So this, people, is your ideal gas equation. And we've got to concentrate in on this R value. So let's figure out what that R value can equal. So if PV equal nRT, then I would take both sides and divide by NT to solve for R. And I would get R equal PV all over NT. So what set of circumstances do you know all the values for? Well, STP. So my standard pressure, I'm going to use 1 atmosphere. My standard volume, I'm going to use that 22.4 liters, and that was for 1 mole of any gas. And the temperature, standard temperature is 273 Kelvin. So when I take 22.4 and divide it by 273, I've got 0.0821. Notice none of the units cancel. So R carries all of these units. Now, these units have some pretty drastic meaning to us in that now, if we're going to use this R, all volumes must be in liters. All pressures must be changed to atmospheres. If you're given grams, it has to be converted to moles. And temperatures, as always, must be changed to Kelvin. Then you can use this R constant. There are other values for R. So if you use the 760 millimeters of mercury instead of the 1 atmosphere, you would get this numerical value. And you can keep doing that. This is if you'd use the 101.3 kilopascals, you would get this value. And it's just easier to memorize one number and know all the units associated with that number and keep using that number over and over and over. So let's take a look at an ideal gas law problem. It says, how many moles of helium are in a 250 milliliter container at STP? So if I have 250 milliliters, I'm going to have to change that to liters in order to use my PV equal nRT. I'm going to divide both sides by RT because I'm solving for N. And I am going to use the pressure of 1 atmosphere because my standard pressure, I want to use the one that's an atmosphere because that's what my R value has. My volume, like I said, I'm going to have to change this over to liters, so 0.250 liters. My R value, 0.0821 liter atmosphere all over mole Kelvin. And times the standard temperature, which is 273 K. So notice the K's cancel here. You get atmosphere, atmosphere, liter, liter. So you have 1 all over moles, which is equal to moles. And so I'm going to take 0.250 times 1, so just 0.250. Divide that by, I'm going to use my parentheses because there's 2 numbers in the denominator, 0.0821 times 273 into my parentheses equals, and I've got 3 sigs working in this problem, so 0.0112 moles is what I'm going to get. And that's the moles of helium. Now there's a second question that asks me how many moles of neon are in this 250 milliliter container at STP. Well, I don't have to rework a problem here. I'm going to use Avogadro's hypothesis that says if you have this gas, any gas, under the same volume, same conditions, they're going to have the same number of particles. So that answer is also going to be 0.0112 moles of neon. So that's how you can get that one without doing any more work. All right, now we're going to go deep underground in a cavern that's pretty large. You can see it contains 1 million liters of methane gas and a pretty hefty pressure there. And so we're going to take a look and see how many kilograms does it contain. So I have to figure out how many grams it does and then change that over to kilograms. If I'm finding grams, I'm really finding moles. And I solved for moles up here, so I'll just use that same equation, N equal PV divided by RT. So my pressure, I'm going to have to take this and divide it by 101.3 kilopascals to get the answer in atmospheres, because I have to convert that over. So I'm taking 1.5 exponent 3 divided by 101.3, and I'm getting 14.8 atmospheres. The volume's already in liters, so I'm good to go using that number. So I'm writing it down. My R value, 0.0821 liter atmosphere all over mole Kelvin. And then my temperature, 315 Kelvin. It's already in Kelvin for me, so I'm good to use it as it is. So Kelvin cancel, liters cancel, atmospheres cancel. I have 1 all over moles, which will give me my answer in moles. So I'm going to take 14.8 times 2.24 exponent 6 divided by parentheses 0.0821 times 315 into my parentheses equals. And I get a fairly large number. I'm going to put it in scientific notation to make it a little bit easier to work with. 1.28 times 10 to the 6th. And it's methane. I got to figure out the molar mass of methane. Carbon weighs 12. Each hydrogen weighs 1. So it's 16 grams per mole. And then I want to change that over to kilograms. So times 1 kilogram is 1,000 grams. So I'm going to take 1.28 exponent 6 times 16 divided by 1,000. And I get 2.05 times 10 to the 4th kilograms of methane. And a large volume of space like that would have a large volume of it. All right, we got one last one to try. And this one's asking me to find the pressure in the sphere. So we have PV equal nRT. This time I want to solve for pressure. So I'm going to divide both sides by V. And so I'm going to take N, which is 19.5 moles, times R, liter atmosphere, mole Kelvin, times T, 621 K, divided by V, which is 685 liters. So 19.5 times 0.0821 times 621 divided by 685 gives me a pressure, 3 sigs working in the problem, 1.45 atmospheres. So you are going to work on completing the ideal gas law problem quiz, which comes up next.